started, and we can have other folks join as they can. So thank you for being here. Welcome to the second session of our BITS Fall 2023 Research Transparency and Reproducibility Series. I'm happy that some of you were able to join last week. If this is your first session, my name is Grace Hahn. I'm the program manager for the Berkeley Initiative for Transparency in the Social Sciences. And this training series, which is generously supported by the Templeton World Charity Fund, is a unique condensed online version of our flagship research transparency and reproducibility training, or RT2, which is typically held over 3 days in Berkeley. I'm extremely excited to introduce today's session, which will be led by Sarah Hoover and Alan Perez of the California Policy Lab. And the session will be called Managing, the session theme is Managing Personally Identifying Information and Sensitive Datasets. And we learned about this presentation last fall and have just been really excited to, and using every single opportunity to include them in our training series. So I'm very excited for you all today if you have not seen this presentation yet. Just a note, if you have questions throughout, please use the chat and I will relay the questions to Sarah and Alan as they're going through their slides. And with that, I'll pass it over to Sarah and Alan for today's session.
Great. Thank you so much, Grace. So we're from the California Policy Lab. We're going to be talking to you all about hashed linkages for administrative datasets today. This work is in collaboration with the kind folks that you see listed below, and it's a process that we've developed over the years at the lab. So just to go through the agenda really quick, we're going to give you an introduction to the lab and hashed linkages, and we're going to talk about the two components of hashed linkages, the hashing and the linkage. And then we'll also share with you some resources, including the lab's code, which we will make frequent reference to during the presentation, and we hope that some of you may end up using it. So administrative data has been used increasingly in quantitative research over the past few decades. And the California Policy Lab has stepped in this area. We work almost exclusively with administrative data. The California Policy Lab, or CPL as we call it, is a research institute based at the University of California, and we have sites both at the LA and at the Berkeley campus. We are a nonpartisan research institute, and our mission is to improve the lives of Californians by generating evidence that transforms public policy. And the key function that we have is hashed linkages. And through these linkages, we have been able to access and work with data from over 40 state and local government partners. And this includes data on wages, taxes, unemployment insurance, human services and homeless system enrollments, health utilization and vital records, data from the criminal justice system, and of course, education data as well, both in the K through 12 and college sectors. So I mentioned that the key thing that we do is a hashed linkage. And what this is a linkage between administrative data sets that preserves privacy and allows us to link on personally identifiable information without us actually seeing it. And examples of this PII are social security numbers, names, dates of birth, things that that will allow you to locate a unique individual and also link. And so there's two components of this. There's the hashing, and then there's also the linkage. So the hashing turns this turns this data into unique but unreadable data. And that's important for many reasons that I'll get into, but really it's to protect the privacy of the individuals in the data. And it's a one-way encryption. It's irreversible, and it allows for the linkage, which is the second step. And because the hashing encrypts the identifiers, consistently across different administrative data sets, researchers can now use those hashes to link the data. And we believe that such linkages between administrative data sets are powerful ways to break down data, research, and policy silos. So I'm going to talk about hashing and what that actually is, and then I'll talk to you about what and how to make that hashing happen. So for the use case, say that there's two agencies. They both have really rich administrative data that you want to use for your research. Both agencies, for a variety of reasons, are unable or unwilling to share their PII. Often it's because of legal reasons, and that's usually the reason that we run into here in California. But there could be other reasons, privacy, security, also trust. The agencies, for a variety of reasons, may not trust the researchers who are requesting the data to actually handle the PII sensitively. And so what a privacy preserving record linkage does is transforms that PII, again, that's social security numbers, names, etc., into encrypted PII. And we use that encrypted PII to make a linkage. And in order to do that, without the two agencies being able to without the two agencies doing it themselves, is for a third party to step in. And that's what we do at the lab. We develop relationships with these two agencies who aren't, for a variety of reasons, are unable to do it themselves, often technical reasons, resources, and capabilities. And we step in as that third party to encrypt that PII and conduct that linkage. So to give you an example of where this actually happened in the case study, so in 2021, through federal legislation and through the California state legislature, the California Department of Social Services expanded eligibility for food benefits, which we call CalFresh in California. And they expanded eligibility to include students with expected family contribution of 0 in their financial aid applications. The California Student Aid Commission, which has these financial aid applications, ran a randomized controlled trial to test the effect of outreach, which informs students on these new eligibility and also encourage them to apply via a partnership with Code for America. They tested they looked to test the impact of that outreach on whether students actually applied and also took up. So the research question they had was, does outreach to college students who are newly exempt from CalFresh student eligibility rule due to having 0 EFC induce them to apply to CalFresh and ultimately enroll? So the challenge is that we have data from these three data partners, CDSS, CSAC, and Code for America. They all have interesting data that we want to look at, but for a variety of reasons, legal, technical, they're not able to do that linkage themselves. And so we stepped in to get data from CDSS and also CSAC to do that encryption. Yeah, so the goal here was really answering that research question. So for example, the Student Aid Commission and the Department of Social Services had information, had names, had where students were enrolled, had their social security numbers, and had a whole lot of other data, and we needed to encrypt that data in order to conduct that linkage. So what this hashing actually looks like, we apply this hashing algorithm called SHA-256. Um, and it actually is a hashing algorithm developed by the NSA, and it transforms these strings of PII into other strings that are completely different from their original values. So some essential characteristics of the hashing algorithm is that there are no collisions, and that means there's unique values between the original string and the hash string. So two distinct social security numbers, for example, will be transformed to two distinct hashes. Um, and if if there's even similar hashes, for example, in this example, you see that the social security number is only different by one value. It'll still produce a unique hash that is completely different. Another characteristic of hashing is that they're irreversible. So there's no deterministic way to reverse the hash to the original value. And because of this, it protects the privacy of the original value. So when we do the hashing and we receive what we call the hash data, we get these hashes of social security numbers, names, etc., but we don't get the original values. And there's no way for us to receive or to deterministically reverse this hash to get those original values.
Just a real quick question, Alan. So someone asked, do you have a templated text that you adapt to share with potential implementing partners to explain this concept? And if so, like, is that something that you could share with this group? Maybe like
Yeah,
after the fact,
definitely.
but yeah.
Yeah, we have a whole toolkit actually that includes code and also a I'll call it a report or a technical breakdown, I think is what we call it, of this whole process. And it talks about it's kind of an expansion of this presentation, but it talks about hashing, talks about linkages, and also talks about working with partners to get this process going.
Awesome, thanks. Oh, one more question. I've heard of hash lookup tables that are pre-generated lookup tables of, say, the social security number and the corresponding hash. Is that an issue?
Um, Sarah, do you want to take this on? But it could be answered by this next slide.
Yeah, I was just gonna say this this next slide is exactly the solution to that very problem.
Perfect.
Yeah, so I said that there was no deterministic way to reverse the hash, but some bad actors could use a hash table, or I haven't heard of that, or could, some other way try to reverse the hash and get those unique values. And so what we do to add an extra layer of security is we hash with a salt. And it's essentially kind of like a password. There are some guidelines that we ask of our agency partners for the SOT. Of course, you don't want it to be like welcome one or something like with the usual password. But for the sake of this example, say that the SOT is I love apple pie. Yeah, no password 123. But say that the SOT is I love apple pie. What we do before hashing is we add this SOT to this string PII, and then we apply the hashing algorithm onto the SOT with the PII. So you see here the social security number. We add to that string the SOT, in this case I love apple pie. Then we apply the hashing algorithm. And this hashing algorithm will give us, because of the characteristics of the hashing algorithm, it'll give us a hash value that is completely different from the hash value if we did it without the SOT. So this like I said, adds an additional layer of security and gives us more confidence in in our ability to protect the privacy of the PII values. So now that I talked about a hash and now that you know what a hash is, I'm going to talk about how to put that into operation. So these are some so it actually takes a while to work with agency partners to make a hash, get data agreements in order and all that. In order to give everyone reasonable expectations about how long it takes to get from the research question to actually even working with the data. On average, at TPL, the process has taken 12 months. Often it's less than that. Often it's more than that. So this is kind of a quick breakdown of how long it what the steps actually are. So there's, at inception, you talk with the agency partners, you draft and sign data use agreements, and then you put together data requests. You learn about the data. You refine that hashing code, which I'll get to in a second. Then you get the actual hash, and then you conduct the linkage process. And like I said, all that usually takes about 9 to 12 months. So we put together some guidelines with when working with a partner. You don't have to follow them to a T, but from our experience, this is usually what works best for us. So of course, at the beginning when you reach out to a data partner and you both agree that you want to work with each other, obviously there's going to be people that you work with, and I mentioned before that trust is often a barrier to getting this data, and we believe that developing that trusting relationship with partners has allowed us to access all this data and is really a key component of developing these relationships and being able to access this data. So a first guideline that we think is important is to be able to put together an explicit data request. And it's important that it's a good data request and specific, particularly when it comes to hash linkages, because the process to transfer data does take longer than a normal data request. So it's important that you're specific about the universe of the data and also the specific variables that you need, and also the specific variables that you want to hash. Some agencies, for example, have addresses and others don't. But if there is the availability of addresses between two data sets between two agencies, then that may be something that you want to use. And so it's important that you know that that is available, and it's important that you put that in the data request. But also, there's other considerations. For example, it could be that for a specific data set, Social Security numbers weren't collected before 2010. So it's important that you talk with the data partner about that and kind of know the specifics of the data before putting together a request. Also, because this hashing the data is a resource-intensive process, we also like to gather kind of information about the operating system that the agency is working with. So, for example, what coding language that they use. We have hashing code both in Python and SAS. Python is, I think, 10 times faster than SAS, but if any of you have worked with government agencies, we all know that they're kind of slow to adopt new technologies, and oftentimes we find ourselves working with SAS. Also their machine environment, are they working in Apple, Windows? And going back to knowing more about the data, it's really important that we figure out how they're storing the data. For example, dates of birth. Um, in order to be able to link the data, it's important that we transform the dates of birth in order to be stored the same way between both data sets before hashing it. So it's important that we learn how they store that data.
Alan, a quick question. How would hashing work for geospatial data? Could you hash the coordinates and still preserve the distance between two coordinates?
I think Sarah is better equipped to answer that.
That's a really interesting question. I don't think we've ever done that. I think what you would have to do, unfortunately, the way hashing works, you would not be able to like hash the coordinates and then later calculate the distance. The way our hashing code works is anything we need that is derived from the values that we ultimately will hash, we derive that in the hashing code and then hash those derived values. We go further into detail on that later in the presentation. So I think what you would have to do is in the hashing code, calculate the distance. We've never, encountered that in practice, but I think that is what would have to be done now.
Cool. So going back to going back to this process. So usually you'll meet with the data partners, get information on the data and the operating environment. This SALT is usually always decided between the agency partners. We set up something like a SALT meeting. A CPL member will join the call, talk about the specific requirements of the SALT, and then leave the call. It's very important that we never learn of the SALT. So we stress to our data partners for them never to share that SALT with us or even other members of their organization who are not directly working with us, because we take the privacy of the data very seriously. We stress that the SALT is only exchanged with people who truly need to know that information. And through these meetings, we also and learning about the data, we also learn about changes that we need to make to the hashing code before sending it to our data partners, and also information that with all data requests, such as how to transfer the data and things like that. And one last thing before we actually hash the test data is that we send them a synthetic test data set, and we develop this test data set after learning about the data, and so we try to develop the test data set to mimic the data, and so that when we apply the hashing code to this test data set, it'll give us some useful information. So to this test data set, we send the code and also the test data set to our data partners. The data partners will input the SALT into the hashing code, and then run the code on this test data set. Like I said, it's important that they don't send us that code back. So we often have to remind our data partners not to do that. But they do send us the test data set. And we're checking for two things here. First, did the code run correctly? Did the code, actually hash the data values, and also, did the code work? If it broke, then there's an issue, and we have to go back and forth with data partners. But a second component is we're testing the SALT. And so when we're comparing the test data sets, we check that the values are all the same. And so we'll be comparing hashed test data sets from two agencies. And when we compare them, they should be an exact match. And if there's not, then usually it's a issue with the SAW being inputted into the code incorrectly, or maybe there is a communication issue with the SAW, and the two agencies believe that the SAW is different. And that's something that we usually just resolve back and forth. So this is an example of a test data set. You'll notice some key things here. For example, date of birth. We're checking for implausible values. So in this fourth row, you see a birth date of 1899. Usually we're working with data past 2000. And so we usually think of values like that as implausible. So in our hashing code, we will actually mark that as a bad date of birth, and we won't use that observation to link. We also test for in names. Oftentimes there's special characters such as letters with accents. And in the hashing code, we transform that. We transform those characters in order for us to hash it. When we talk to our data partners about the specifics of the data, we do ask them what special characters are included in the data, because it's important that during the hashing process that we catch those characters, because like I mentioned before, if even just one character is off, the hashing algorithm will give you a completely unique value. And I'm just going to give you a quick rundown of what our hashing code does. So like I said, it normalizes the data. So it converts, say, like special characters into same values between both data sets. And then we remove white spaces, punctuations. We kind of try to just minimize any errors. Because of the hashing algorithm, because we cannot see the original values, it's really important that we do this standardization process, because we want to be able to match, get as many true matches as possible. For reasons that Sarah will get into later, we also chop up the data into PII partials. So like, for example, we grab the first two letters of the last name. Like I said before, we also add the salt strings to the data, and then finally we hash the data. We use this SHA-256 algorithm. I think it's very widely used, developed by the NSA or in partnership with the NSA or something like that. But from that, yeah, that's basically what our code does, and we'll show resources to it and or links to the code later on. But now that we know what hashing is, I'll leave it up to Sarah to talk about what we do after the hash.
Awesome. Thanks, Alan. So as Alan mentioned, we take the hashing process is really about taking the personally identifiable information and transforming it so that once we get the data, don't actually have access to those underlying values. But the ultimate goal that we're trying to do is to use that data to link with other data sets. So I'll go into what that actually looks like. So just to kind of restate the problem here, imagine we have data from two different hospital systems. They each have data on the first name and the last name of the patient, but we can't, we're not allowed to actually see that data. So how are we able to link these together? And the answer is to do a hashed linkage. And note in this case, both hospitals have their own unique identifier. You know, this is patient number 1234, but when linking with different administrative data sets, each agency likely has their own identifier, and that might be able to be used within an agency, but can't really be used to link across agencies. So that's why we rely on the actual PII. And just to give you sort of a view into what this actually looks like, in our case, we can't actually see that the underlying values of the hashes are John Smith. We see something like the blue characters below, but then we can see, okay, this blue character matches this blue character, and the last name matches as well. So even though we can't, directly observe that this is John Smith, we can say, okay, these two observations have the same first and last name. We think they might be the same person. So the basic idea of what we're trying to do is we request an unhashed identifier from each agency. The agencies choose a salt. We have them hash the PII. Both agencies send us back the data, and we just join the two data sets on the hashed PII field. And the final result of this is what we call a crosswalk, which is basically just a mapping from identifier A to identifier B of who is the same across these data sets based on what we think. And once that's done, we can use that crosswalk to merge the data sets together and do our analysis, and we don't need to use the hash data after that point. So to make this a little bit more concrete, in the previous example, this is what our actual data would look like during this process. We can't actually see that this is John Smith, but we see, this person has the same first and last name as this person, and same here. So we say, okay, looks like these are a match. And then our final output is this crosswalk where we say, okay, based on this linkage that we did, we see that 1, 2, 3, 4 in agency A is the same as person 7, 6, 5, 4 in agency B. And this is what the final crosswalk would look like after conducting a linkage.
Quick question, Sarah. So is hashing different from adding noise to the PII variable?
Yes. I'm trying to think. It is different from adding noise. I don't know too much of the specifics behind the cryptography of it, but it is supposed to make it completely irreversible. And it's not just a little bit of noise, and it preserves exact equality. I think if you add noise, it's possible there might be some difference in agency A to agency B. And hashing is supposed to be, if you hash the letter A, it's going to be the same no matter what. And that's kind of the important property we're able to use to then link the data. Awesome. So yes, our final output will be a crosswalk where we can match these identifiers together. So that's sort of the simple version, but as researchers, we all know things never really work out that simply. There is typically issues with the underlying data, right? So imagine if someone's name was mistyped in one data set. In the previous example, we wouldn't be able to identify kind of the string distances to see who's the same, or, are these values close enough? And there are also many other cases you can think of, right? There's typos, there's people's names might change. There's just nicknames. So, in one data set, it might be John versus Jonathan. So how do we actually use this process to account for these types of differences? So just as an example of what I'm talking about, Here we think these two people, looking at the raw data, we can sort of intuit, oh, I think these might be the same person. They have the same social security number, the same last name, and the first names are only off by one letter. So that looks like it might just be a typo. This looks like the same person. But once we hash the data, we actually can't see that the first names are really close. So our approach to this is to extract certain features from the personally identifiable information before we hash it. So in the example of first names, our code, before it hashes anything, will first separate out the first letter of the first name, the first 4 letters of the first name, and also a few other things. And in addition to hatching the full first name, we also hash these partial values so that we can do kind of smaller comparisons once the data are actually hashed. So in this example, we think John Smith and Jonathan Smith might be the same person. As you can see, the full first name, if we had relied just on that, is completely different, and we'd have no way of knowing that there is actually a relationship between these underlying values. But once we take the first letter or the first 4 letters, we are able to see that there is a match. So in practice, there's kind of a standard set of personally identifiable information that we typically receive. This is by no means exhaustive of everything that we have received or could possibly received, but based on our experience, the most common fields tend to be social security numbers, first names, last names, and dates of birth. And we have these fuzzy fields are the partial strings that we extract from each field. And for names, we typically take the first letter, the first 2 letters, the first 4 letters, and something called the soundex. The soundex is meant to be a phonetic transcription of a name, so that if it's really meant to capture how the name is actually pronounced. So in our previous example, Carlo with a K versus Carlo with a C would have the same soundex value because they're actually pronounced the same. For social security numbers, we'll take 8 substrings of the social security number. And the way we do this is we take the full string, remove each pair of 2 consecutive digits from that string, and hash what remains. So that ends up being 8 substrings of the social security number. And for dates of birth, we'll hash the month, the day, and the year all separately. So let's look at an example of how this might actually work. So here,
Sarah, sorry, could I jump in with one question? I think that was about the last slide. So are there privacy concerns to crosswalking multiple data sets? By combining multiple data sets, we have more information about a person, and the combined information could perhaps reveal the identity of a person.
Yeah, absolutely. I think that definitely is a concern, and is typically something that is addressed kind of in the first stages with a partner when we're coming up with this this methodology. And it, I mean, yeah, it definitely is a concern. I think kind of our philosophy is to request the minimal amount of information from each partner that we need to do our research. Of course, that can still, as you point out, even when we're, even if we do that, that can still, you know, point to issues. The main kind of the main thing that our solution solves for is that we can do a linkage without directly observing the PII. And, you know, if there were, like, say, a data hack or something, you know, someone's not going to be able to actually observe the PII. But, you know, kind of your other concern about, you know, is there just too much other information that someone could reverse engineer is definitely still a concern. I think the sort of ideas we try not to do more than we need to. Yeah, I guess that's not really a satisfactory answer, but we kind of just do the best we can.
Awesome, thanks.
So let's look at an example of how we would actually use these partials. So this is what our data might actually look like in practice. So we can see, okay, the first names alone are different. However, we see the first letter, the first 4 letters, and the last names are all the same. But do we really think this is enough to conclude it's the same person? So in this example, it actually turns out that we have a Samantha Smith and a Samara Smith. And even though they do have the same first 4 letters, that doesn't really seem like it's the same person. So how do we account for false positives while also allowing for kind of fuzzy matches within our data? And the way we do this is called a matching round. And these are a set of criteria that we use to determine who we think is a potential match. And it's really important that each field is evaluated in the context of the other fields that we have. So in the last example, maybe the first 4 letters of the first name and the last name on its own, that seems a little dicey. However, if that observation also had the same social security number, that would definitely make us more confident that that's the same person. So some examples of rounds that we've used in the past are just a perfect match on all PII. But as I mentioned, we also want to introduce, you know, some variations, allowing for some fuzziness in fields. So another round that we typically use is a perfect match on social security number, and a perfect match on 2 of the other remaining fields, and a fuzzy match on the third. And in this process, we also will score, we will assign a score to each potential match to identify how strong we think the match actually is. So anytime we're evaluating a comparison between fields, we'll assign that potential match a score. So a match on the full value, the full hashed value. So for example, the full first name will have the highest score. But then there might be other ways, you know, if it's a match on the soundex as well as the first 4 letters, that's maybe the second strongest match, and then maybe a match on soundex alone is then receives a slightly lower score. So we have to think through all of the possible ways we want to combine these subfields and, you know, compare them and think which one do we think is really stronger than the other. And I think the really important takeaway from here is just that each field on its own, you know, the first 4 letters of the first name, if that's all that you were doing, that definitely wouldn't be enough, right? But the first 4 letters of the first name in the context of all this other information can help you make that final determination. And we also have a few ways that we tend to assess how well our linkage actually went. It's pretty difficult to do this because we don't have access to ground truth data. You know, if we knew what the true matches were, we would just use that in our analysis. So we have a few other ways that we tend to think about these things. So one way of doing this is to evaluate on the other fields that we have available from each agency. So say we have income both in dataset A and dataset B. Once we identify our potential matches, if we're seeing that in people that we think are the same, they tend to have the same income across those two data sets, that's a good indication that we found the correct matches. However, if we're seeing that the income tends to be very different, that might be an indication that we've found some false positives and might need to rethink some of our matching criteria. Another way we tend to think about this is by measuring the rate of IDs in one data set that match to more than one ID in another data set. So if we trust that ID that the agency gave us, that it's identifying a unique person, if we see that one person in dataset A is matching to multiple of those IDs in dataset B, that means they're getting matched to multiple people, and that's an indication that there might be some false positives in there. We also tend to find that, based on having done this a few times, that the majority of matches tend to be found on the most strict round that we do. So if we're seeing a larger spike later on in the process in the number of matches that we pick up after after loosening some of our criteria, that's an indication that there might be some false positives as well. And now I'll go into how to think through your linkage strategy. It really has four main components to think through: what PII you have available, what partials you want to take, definitions of bad data, which I'll go into in further detail, as well as identifying the scoring function that you want to use and coming up with your matching rounds. So the linkage strategy really starts before you even hash the data. So you have to think through what PII or other information that I can link on is available in both data sets, and what partials do I want to use, do I want to extract from that data. And that's a really important to be thinking that through prior to the hashing, because all of that kind of extraction is done during the hashing process. The other piece is to identify what we consider to be bad PII. So as Alan mentioned in a previous example, there are certain cases where we think there's invalid data, and we don't want to use that to link because that might result in a false positive. So things like an implausible birth date, is it too far in the past or too far in the future? With social security numbers, if it's more than 9 digits long, that's an invalid security number. There also might be, it's important to really understand in depth with each partner as well, because they might have placeholders that they're inputting for missing values. If they're putting in, 111111 for a social security number that's really missing, we don't want to then hash that value and link it to the other data set, because that's not a true valid value as well. And so thinking through what constitutes bad data is also a really important part of your linkage strategy. And this can be challenging, more challenging than you might think. For example, what do you think constitutes a bad address? When we were first thinking about this question, we thought maybe a non-numeric street number could be an issue, but then we thought of something like 11A Main Street could be a valid address. So you want to really think through, with your knowledge of the data set, what could possibly be in that data and think through possible edge cases as well. Another note is that we don't actually hash data that has been flagged as bad. The hash strings take up a lot of space in computer memory. So, if you don't want to use the bad values to link, there's no point in hashing it and keeping that value around. So we'll kind of just blank out those values and have a marker saying this was a bad value. And I mentioned scoring recently, but that's another key part of determining your linkage strategy. And it's how we really quantify the quality of a match on a given PII field. So you'll want to think through what are all the possible combinations of the different partials that I'm extracting from this field, and which ones do I think are the strongest. The last, but definitely a very important part is determining the matching round, which are the actual criteria you'll use to determine who you think is a match between data sets. And typically, we recommend coming up with multiple sets of criteria and then ordering these from strictest to loosest, and then kind of using that to evaluate, okay, if I loosen up this one requirement, how many additional matches do I get? And that can kind of inform if you think you're getting too many additional matches, maybe you'll try again and remove that round. But doing it that way gives you visibility into what's actually happening under the hood in your data. So we've gone through a lot in our presentation today, from the hashing to the actual linkage. And we do have, as Alan mentioned, we do have a toolkit, including our code, that is publicly available for anyone to use. And in that part of that code is we have defaults that, based on our experience, tend to work pretty well with most administrative data sets. They use kind of the standard 4 PII fields that I mentioned before that we think tend to be the most common. And we include a set of 4 rounds by default. However, the defaults are all there. However, the code is intended to be customized however you would like. So this is certainly a good starting place, but by no means, if you're interested in doing this kind of work, by no means is it the way you have to approach it. So just a look at what our default rounds actually are. So we order them from strictest to loosest. The strictest round is a perfect match on Social Security, first name, last name, and date of birth. The next one is a perfect match on Social Security, 2 of the other fields, and a fuzzy match on the 3rd field. And the next round is a perfect match on Social Security and 2 of the others, but not requiring the 3rd to be a fuzzy match. The 3rd could be entirely different. And the last round is a perfect match on Social Security and 1 of the other fields. And you'll see here, we also noted which observations we would exclude from the list of potential matches based on if their PII is bad or not. And typically you'll want any fields that you are requiring to be a match. So in round 0 and round 1, we use all of the fields as matches. So if an observation has bad data on at least one of those fields, it wouldn't be included in our list of potential matches. So just to go over what we've talked about, the linkage strategy really starts from the beginning before you even submit the data request. It includes the PII fields that you want to use, as well as the partial fields that you'll extract and the criteria you're using to identify bad data. Then it's a description of how to score each field. And finally, the list of match criteria or rounds that you will use to actually link. And as I mentioned previously, it's important to do this before hashing so that we get everything we need from the data before the hashing algorithm is applied. So just to dive a little bit deeper into our actual linkage code and what it really does. So the output of our code will be three main things. So the first thing is what I mentioned previously, the crosswalk, which is pairs of IDs that we've identified as matches. And it also produces a few other things that are meant to provide some summary statistics to help you when you're trying to evaluate how well the linkage actually went. So this is what the crosswalk looks like, and it will also include the round that those IDs matched on and the score that they received. As I mentioned, there's two other outputs with summary statistics. So the waterfall is how you identify how many additional matches you're getting at each stage. So in this example, you can see we got around 6,000 matches, new matches by introducing round 4. And this sort of exemplifies why it's critical to order your matches from strictest to loosest. So you can see, round 4, I just loosened up one requirement, and that one requirement gave me 6,000 new matches. And the round summaries will have a few other things, such as the number of IDs in one data set that matched to multiple IDs in the other data set, the number of IDs in total, and some other summary statistics as well. And an important note is that there is before actually conducting a linkage, there is some groundwork that needs to be laid before the code will actually run. So this includes things like renaming columns. If there isn't an identifier provided by the agency, you can certainly use one or create one yourself. We usually recommend doing this using row numbers in some fashion. And so in terms of column renaming, the code expects certain fields such as social security number to have specific names. And also it's important that any field you're trying to link on has the same name between the two data sets. So there's a few other troubleshooting things that may come up in the process as well. We've seen some people run into memory issues before. The data sets administrative data sets are often very large, and the hashed strings take up a lot of space. So this is definitely a very memory intensive operation. Something we've seen done successfully is breaking up one of the data sets into smaller chunks, and then successively linking each smaller chunk to the other data set. And at the end of it all, appending the resulting crosswalks together. Also, just a note is that our code does not restrict IDs to a single match. So it can certainly be modified to do that as well, but kind of just a note. And it's primarily designed to link data from two data sets, but it can be expanded to use multiple as well. And the activity we sort of assumed there wouldn't be time for, but we can share the slides with you at the end of all this. And the the activity is really just to give you an example of how you would think through having multiple data sets, you know what data they have, how you would think through creating your linkage strategy. So that can be a good exercise for you if you're interested in that on your own time. And just finally, for takeaways, hashed linkages are a way to break down data silos while preserving privacy, and can help answer policy and research questions. And we have links to all the resources we mentioned. We'll also share these slides with you so that you know, don't feel like you have to quickly get your phone out and take the QR code now. You'll have time at the end of it all. And yeah, thank you, everyone.
Thank you so much, Sarah and Alan. And yeah, again, as Sarah mentioned, we'll share these slides and the recording as well. And you can always reach out to us with questions and we can, you know, try to relay them to the CPL team. But yeah, I just want to quickly remind everybody that we have another session on November 29th, which will be about the intersection between data sharing and code. It'll be more of a hands-on training for version control using GitHub. So thank you, everyone. And thanks again, our friends at CPL, and hope you all enjoy the rest of your week and your weekend. Take care.
Thank you. Bye.
Thank you, everyone.